So last time we speak about levels of measurement, and a week before we focused on measures of center or measures of location. So the mean value, median, and so on. And all of those measures show us, in some sense, where our data is as a whole. So in fact, we have several data points, maybe tens of them or hundreds of them, and they are all spread out all over the place, but we can find the so-called center. Well, it's not always the true center, but it's somewhat, how do I call it? Somewhat center-like, if I can say so. So mean value, the median, the mode, they all show us where our data is. But there is another important property of our data. So as I already said, the data is spread out over some interval or something like that, and we need to know how is it spread. So we need some measures of spread, and we have already seen two of them. So we have range. Let me put it here. We have range, which is just maximum value minus minimum value. And we have interquartile range, which is third quartile minus first quartile. Both of them are measures of spread. So they show us how wide is our data dispersed. And there is one more. So we already told about mean value. So mean value is something like the center of our data. And one question that might be interesting for us is how far are our data points from that center, from the mean value. So here I have a small toy data set with only 5 entries, and we will use that as an example. I went ahead and I found the mean value, and here in this column we have something we call deviations. So deviations, that's just each value minus mean value. So 35 minus 41 minus 6, 37 minus 41 minus 4, and so on. So these are, in some sense, these are distances from the mean. So these numbers, deviations, they show us how far from the mean our values are, our entries. But they are different. So each entry has its own deviation. And I would like to do something like we did with mean value. Maybe we can find mean deviation, right? So to find the mean of these deviations, I will first have to add up all of those numbers. And if we add them up, in fact, let's do it right here. So we can use just the Excel's inbuilt sum command. So I'll ask Excel to sum up all of these values. And we get 0. So let's check manually. Minus 6, minus 4, minus 1, plus 2, plus 9. So before I go ahead and calculate it, let's try to calculate it ourselves. So minus 6 minus 4 is minus 10, minus 11, minus 9, plus 9, 0. Yeah, it's right. So the sum of the deviations is 0, and it's not some kind of lucky accident. So if we move to another data set, like this y points here, they have the same thing. So if I find the sum of all the entries of the deviations, what I get is 0 again. So that looks like the general rule. General rule. So sum of all the deviations is always 0. Deviations from the mean. Let me put it here, because you can have deviations from the median in some situations. Okay, so I can't find the average. Well, in fact, I can find it, but it will be always 0 because the sum is 0. So if I add those numbers up, it will give us 0, and 0 divided by anything is 0. So the average or mean deviation is unusable for us. It will be 0. And I can see why it will be 0. We have some points which are larger than mean, and some of them are smaller than mean. So the deviations are either plus or minus, positive or negative. And the negative ones balance out the positive ones, and the sum is 0. So one way to fix that will be to get rid of those signs, negative signs. And one way to do that is taking the absolute value of the number, so the modulus, right? We can use, I'm not, okay, it's working, and I was not sure if my keyboard allows it. So we can use this instead of just x minus mean x. Oh, by the way, yeah, okay, so let's leave it like this for now. So we can use this. We can use absolute values or modules. However, it's more, well, how do we put it out? It will be more convenient for us to instead do this. So instead of an absolute value, I will take the square of deviation. And the square of any number is always positive. So we will get rid of those minus signs. So let's go ahead and do it. So I need to take the square of this column. And now I have all the squares, and you might propose to find their average. So add them all up. Let's do this now. So we have 138. And next step would be, if we were calculating the mean value, our next step would be dividing it by 5, because we have 5 numbers here. But here, it's not the case. We will divide by 4. And let me put it in this way, 5 minus 1. And now we will see why it is so. Yeah, let me add a row. Okay. So why 4? Why not 5? We have 5 numbers, 5 entries. So we have 5 deviations and 5 squares, but we are dividing by 4 for some reason. Well, here is the reason for that. You can look at it like this. So do we really have 5 random numbers here? The answer is no, because we have already seen that all of those numbers need to add up to 0. no matter what data I use. So they add up to 0 here. They add up to 0 here. We can in fact just generate some totally random numbers, and let's do that. Why not? So I'll ask Excel to give me random numbers between maybe 1 and 10. And I'll create another 5 of such numbers. And I'll find their mean. All of this. And their deviations. So this is A17 and this one is A22. And then we will add them up, all of those deviations. 0. No matter what numbers you have, deviations from the mean will always add up to 0. So you can see the numbers change, the deviations change, mean value changes, but the sum is always 0. Okay, so the sum of our 5 deviations needs to be 0, but that means that one of those deviations is not the number we can freely change. So we can, in some sense, we can change these 4 numbers however we like, but choosing first 4 will define in a unique way what must be the 5th, because we need to have their sum equal to 0. So let me put it here. Okay, I will use D for deviation. In fact, they usually use Greek letter delta, but I'm just too lazy to go search for an injured symbol here. So we will use D for now. So we need to have this dx2, dx3, dx4, and dx5 equals to 0. Statistics tells us. But that means that our dx5 will always be minus dx1, dx2, dx3, dx4. So those numbers are not independent. If you choose first 4 in any way you want, then your 5th one should be this. You can't change the 5th one freely. So you can only freely change, independently change 4 of them, not 5. Because the sum of deviations should be 0. And that's why here we divide by 4, not by 5. If we had 20 numbers here, then we will divide by 19 here. So that's the reason. So let me put it somewhere here. So we have a thing that's called df. Yeah, okay, I'll put it here. df, degrees of freedom, and it's equal to number of, so yeah, number of all the entries minus 1 when we are calculating the deviations and so on. There will be cases where it will be minus 2 or minus 3 because you will have more conditions than just this one. So the general formula or general rule will be like this. So number of entries minus, entries minus number of conditions. And here we have only one condition, this one. The sum should be 0. So number of entries is 5, number of conditions is 1. That's why 5 minus 1 here. So this thing we got in some way shows us how far our numbers are spread from the mean value. However, there is still an issue. So let's imagine that these are maybe ages of different people. So they will be measured in years if they are ages. Now, I want to write it here. I'll put it here. So this one is in years, and our deviations are also measured in years, but here we squared them. So now the unit for these numbers is not years anymore, it's years squared. Or for example, if they that was prices, here the unit will be something like sum or dollar or euro, maybe euro, why not put euro? And the deviations are also in euro, and here we have euro squared. Or maybe this is just a number of apples in a box, so 35 apples and the mean is 41 apples, so 35 is 6 apples less than the mean, and then all of a sudden you have 36 squared apples. That's, well, not that it's meaningless, but it's not applicable to our everyday life intuition. You never see squared dollars, squared apples, and so on. So I want to bring units back into normal. So if this is number of apples, I want number of apples here, not squared number of apples. If this is in euros, I want to have euros here instead of squared euros. So to get rid of that square, I will take square root of this thing that we found. And we will call that thing standard deviation. So usually it's denoted by S. And because it's standard deviation of our x, I will put it like Sx. Okay, so that's standard deviation. So what does that mean? What's the meaning of that number? We know the mean, it's 41, and standard deviation tells us that our data entries are approximately 41, right? So we can approximate them just presuming that all of them are just equal to 41. But if you want to be more precise, you can say that, well, all of them are nearly 41, and their difference from 41 is around 5.87. Oh, and by the way, let me round that. We don't need 5 numbers after the decimal. Yeah, I clicked the wrong button. It happens. So number format, and maybe we can just leave 1 decimal place. Okay, so approximately 5.9. You might have seen sometimes in scientific literature, you can see something like, well, for example, the measured mass of the object was 47 plus or minus 2 solar masses. And that 2 after plus or minus is connected, has deep connections with this standard deviation thing. So that's standard deviation. Let me write it down here. standard deviation, and it shows us how far our numbers are from the mean. Okay, so let's move to this data set and do the same there, because I want you to compare one thing. So h5 squared and then I'll take the sum of all those, and I'll divide by 4 again, and I'll take square root. So this will be standard deviation for y. So I'll mark it as sy as opposed to sx. So sy 5.5. Now, if you look at those two numbers, this one is larger, this one is greater than this one. And also, if you look to the data itself, you might notice that they have the same minimum and the same maximum, and even the same mean, right? So if I was going to find range for x, it would be 50 minus 35, 15, and for y, it would also be 15. And the mean values are the same. So when you are describing your data, if you only tell someone the mean value, the range, the median, it is also the same. As you can see, it's 40. The range, the median, and minimum and maximum numbers, that person will not be able to know if you are talking about x or y, because they have the same mean, same median, same minimum maximum values, same range. But there is a difference between them, and well, and let us even visualize it. So I'll put a picture here. I guess column would be enough, or not, maybe line. Yeah, let it be line graph. I'm not sure if I can mark both columns in, yeah, online version of Excel does not allow me to do that. Okay, I can just copy them here. I want them to be on the same graph. Okay, and this one too. And now we will put a line graph here. With points, I guess. Yeah, so you see, these two, they start and end at the same points. They have the same center. They span the same space from 35 to 50, but they are different. One of them is changing more than the other. Yeah, so here you have that neat plateau in the middle where there is almost no change. This part where you have 3 40s in a row. So first one is changing more fast than the second one. And the first one is has larger standard deviation. So we can say that this standard deviation thing shows us the amount of change in our data. So if you have larger standard deviations, then you can be sure that There are more differences between different data points in your data. And that's exactly the reason for a naming, because we have a name for this thing, which is square of standard deviation. And it's even denoted just S square, but it has its own name, and that name is variation. So I guess you know the meaning of the word. Variation is, well, to put it crudely, variation is a change. And that's why we call this thing variation. And if you take a square root of variation, you get your standard deviation. Both of them show how far your data is spread and how prone to the change it is. When there is less change, you have less variation and less standard deviation. Okay, not sure if we need this chart. Let me go ahead and delete it. You have already seen it, I guess. And if you want to see it one more time, you can just go to the YouTube, start the recording, and pause it at this moment. Okay. So sometimes, even though your data looks strikingly similar, you can still spot the changes. And one way to do that is using your standard deviation. Okay, what else? So there's something I should... Ah, yeah. So there is a thing called Chebyshev's theorem, but I think we will make a pause now for about 5 minutes. So you can go take a bit of a fresh air, or maybe drink some water or tea or whatever. And then we will continue with Chebyshev's theorem and with how all of this is connected to probabilities. So be right back. So there's a thing called a Chebyshev rule. And I guess we better look at some real life examples for that. Oh, not real life examples, but some examples. So, but first I will bring my cells back to normal. It was 11. Okay, and oh well, doesn't matter. Let's just put our numbers there. So maybe okay, 0. I don't know, 4, it doesn't matter in fact. Any random number will suit us. So I want the large data set, because small data sets with 5 or 10 entries won't be enough for that. So let's take 20 numbers, 20 random numbers, as you can see here, and I'll go and find their average or mean. So it's A1 up to A20, I guess. And to find standard deviation in Excel, you don't always have to do all this stuff. There is an inbuilt formula. So std ev point s. So there is also stdev point p. We will come back to that in a time. So you can just use this formula on your numbers, the numbers themselves, not deviations. And it will calculate you your standard deviation. So here I have it rounded to 1 decimal place. That's why it's showing 5.9. But if I copy it and paste only the value, you can see that they are the same, 5.87 and so on. Okay, so now I won't do all that boring stuff with finding deviations and so on. I'll just ask Excel to calculate standard deviation for us. So A1 up to A20. And now I want to do one thing. So this is our M and this is our S. And I want to find how many numbers are between M minus 2S and M plus 2S. And it will be good if I sort my numbers first, I guess. So again, data sort ascending. No, just sort. Okay, so my mean minus 2 standard deviations. Well, in fact, I guess I won't calculate that manually. I will again use Excel, and first I will change my format. I don't need all those decimals after the dot. Okay, so here C1 minus 2 times C2 and C1 plus 2 times C2. And again, let's round them to 2 decimals. That will be enough. Okay, so I want to find how many numbers are there between 12.12 and 23.98. So all of them are larger than 12.12. And yeah, that's kind of large number. 19 out of 20 is between those two boundaries. So 19 over 20, let's remember that for now. Let's take another data set, another example, and do the same for that. Maybe I'll put them here. So I just asked Excel to create some random numbers between 1 and 50. Again, I'll take 20 of them. I'll calculate mean and standard deviation for those. So mean and standard deviation. Average of K1 up to K20 and standard deviation of K1 up to K20. Oh, and again, we need to adjust the format. And I'll find these two things, M minus 2S and M plus 2S. So M1 plus 2 times M2. Oh, it should have been minus. And the same with plus. Okay, so we need to count the numbers between 1.05 and 56.8. That will again be a large number. What? Okay. I'm all right with that. just sort. So they are all larger than 9 and they are all less than 56. So we have 20 out of 20. 95% in one case and 100% in second case. And maybe we are just lucky in these circumstances. Maybe what we need to do is look at some other random data. So let me just show you how this data look. So I'll put a histogram. Okay, so that's our first data set, and you can see that it's mostly concentrated towards the smaller end to the left, and there are some outliers. And our second one is more or less uniform. So here it is. And in both cases, we see that almost all of our data lies within two standard deviations from the mean. It's not always true. So I'll take third example now. Oh, I'm entering it in the wrong way. Maybe, I don't know, maybe 30 and 5. I'll do 20 numbers again, just because it's easier to calculate. Oh, and yeah, and I'll change the format. I don't need 5 decimals. Why? I guess I changed it, but okay. Yeah, good. So again, average of all those A22 up to A41 and standard deviation A22 up to A41. Oh, and yeah, that's again copy, paste just the numbers and sort them in advance. We will need them sorted. Okay, so here again the format. And those boundaries of two standard deviations. So it's C22 minus 2 times C23 and C22 plus 2 times C23. Okay, so between 20.8 and 40.5. Oh, okay, again, all of them. We are lucky today. So you can see that it's a big percentage of our numbers. 95% here are within two standard deviations. 100% here and here are also within two standard deviations. And we can do something like, I'm not sure if I'll be able to generate bimodal distribution, but I'll try. So, oh yeah, I wouldn't be able to do that. I'll have to do it manually. Well, okay. Okay, I'll do 22, 22, 22 again, and maybe 23 and 30 and 40 and then 55, 56, 57, 57, 57, 60, 62. Well, why am I even doing it manually? But okay, I have no choice. So 3, 3, 1, 7, 3, 3, 1, 7. So let me move all those numbers here and let me, yeah, let it be this way. And let's put the histogram right away just to see what kind of data we have. Oh, it shows it in a wrong way. But okay, whatever. You can see that most of our numbers are either to the left, to the smaller side, or to the right, to a larger side. And there is a very few numbers in between, 30 and 40. Here are our boundaries. And again, all of our numbers are between them. Okay, 100%. And there is a rule. So if you take mean plus, so we already used n, right? Let me use z for that. Z standard deviations and mean minus z standard deviations. So percentage of numbers which are between these two, or in fact, I guess it's better to do it this way. X and smaller than m plus z standard deviations. So percentage of numbers between those two will always be either equal to or more than 1 minus 1 over z squared. So here in our example, we took two standard deviations. And if I substitute 2 here, it will give us 75%. Yeah, 0.75. So at least 75% of your data will be within two standard deviations from the mean. And it doesn't matter what kind of data you have. So here we have something that looks like a bell. Here we have something uniform and so on. Here we have another thing. And in all the cases, you have more than 75%. You have 95% here, 100 here, and 100 here. And in part, that's caused by our data being small. We have only 20 entries. If you take something like 100 numbers or 1,000 numbers, then it won't be 100% always. It won't be 95%, but it won't be less than 75% for two standard deviations. If we take 3 standard deviations, at least 89% will be between mean plus 3 standard deviations and mean minus 3 standard deviations. Almost all of our numbers. So it's almost 90%. And if we take 4 standard deviations, it's 94% or more, and so on. Well, let me just try to reproduce that with larger data set, because number of times where you will deal with sets of just 20 numbers will be very small, and it will be better if we can sometimes practice with larger ones. I don't know, maybe 50 and 5, or maybe 50 and 15. It doesn't matter, in fact. Okay, let it be this way. So I want 100 numbers, and I still think that 100 is not enough. But, oh, and yeah, and I guess I don't need a perfectly normal distribution. That will be That will be counterproductive. Now it's okay. So again, don't pay any attention to the exact Excel formulas. I'm using them just because I'm too lazy to create 100 random numbers by myself manually. So I'm just asking Excel to do that for me. Let's round. So I need mean and standard deviation, and my mean is okay, so now it's here, and I'll copy this. Oh, okay, that's wrong. That should be J12 or 10. And my standard deviation is again A1, J10. So here we have our mean and standard deviation. And again, I'll find those boundaries, mean -2 standard deviations and mean +2 standard deviations. Now, we definitely do not want to count it by hand. So again, I'll ask Excel to calculate how many of them are between those boundaries. So I'm just telling Excel, count everything between A1 and J20, which is more than or equal to whatever is in this cell E12, and whatever is smaller than or equal to this. Oh, something went wrong. I'm not sure what.
Teacher, why there is J20, not J10?
Yeah, it should be J10. It should be J10, but it's still counting. Oh, okay, now it's all right. So 93 out of 100 is between those boundaries. So it's still more than 75%. And if I change that to 3, then my percentage will go up. Yeah, 100% now. So that's the Chebyshev rule. If you go Z standard deviations from the mean to the left and to the right, then between those, you will always have this much of your numbers. Again, you see, even 100 is not large enough to give us smaller percentage. It's still way more than 75. But when you deal with very large data sets, like maybe thousands of numbers and so on, you might sometimes have closer to 75 for 2 deviations, or closer to 89 for 3 deviations, and so on. But you will never find less than 75 or less than 89, and so on. And you know, it's already 240. I was thinking that we'll look at idealized mean and standard deviation, but it's already almost 2 hours, and I guess you guys are tired. or bored. So maybe we
No.
will stop here. Sorry?
Now you can continue. We are not tired.
Okay. Is everyone on that side?
No, come on.
I would much prefer to finish it today, meaning to finish the topic
Yes, there
today
is much
instead of
information. It is
instead of
difficult
breaking
to
that.
get
But
all
yeah,
of them all together.
okay, then we will do this. We will stop now, and later this week I will upload the pre-recorded video with missing parts of the topic. So there is a thing left, which is how you can use probabilities to calculate your mean value and your standard deviation. And that will also explain what's that second standard deviation in Excel. So you see you have two here, S and P, and we were only using S. But okay, we will leave it out, and I will create separate video without any live meeting, and I will upload it to our playlist on YouTube. Maybe tomorrow, maybe on Friday. Okay then, so maybe if you have any questions, I can answer them now. And we will finish.
Actually, we don't have any question about the topic.
Okay. In case you remember anything,